start talking a little about math. Okay, we're going to start talking about massive stars in the beginning mostly. So let's start. What are massive stars? Many of you are working on this. Some of you might be outside the field. So in the field, when we talk about massive stars, we talk about stars that are initially more massive than about 8 times the mass of the sun. This is where we think that stars would undergo through all phases of nuclear burning until they eventually develop iron cores that collapse to form either neutron stars or black holes. And which stars form neutron stars and which stars form black holes is not something we actually know. This is one of the big questions that we have in the field. Massive stars have a lot of properties that I'm not going to talk about today. Maybe I should mention that they're very rare objects. Nature doesn't really like forming them, but they kind of make up for this by being extremely hot and luminous. So they are very important sources of energy for stellar feedback, for creating elements, for creating energy and feeding the host galaxies with energy. One of the things that I am going to focus about today is the fact that the majority of massive stars are actually found in binary systems or in multiple systems. This is, in fact, how I started getting involved in the field. Originally, I wasn't so interested in binary phenomena, but it's kind of unavoidable when you work in this field. So what I do in my research is mostly to look for different types of binaries that represents different evolutionary phases of such a binary system, and we'll talk a little about this. We think that something like 70% of the massive stars would interact with a companion star during their lives, and we'll see how these interactions look like in a sec. So my main question that kind of guides my research is how do these massive binaries evolve? I also focus a lot on subsolar metallicity or low metallicity conditions, conditions that are a bit closer to those of the early universe. But it turns out that this question is really fundamental for a lot of the other things that many astronomers, maybe some of you as well, are interested by. For example, the occurrence and properties of stellar explosions like supernovae are completely dependent on our understanding of binaries. Stellar feedback and star formation and even planets, they have a very strong synergy with the evolution of these massive binaries. The black hole mass spectrum, all the way from stellar mass black holes to supermassive black holes, are governed in a large sense by these kind of interactions. And finally, something that will guide the talk a bit today is gravitational wave physics. So I don't know if many of you or some of you are working on this field, but it's a very hot field right now. It's a very exciting field. We are detecting these gravitational wave events coming to us from the far reaches of the universe. They're coming from the merging events of black holes and neutron stars in the in high redshift universe, and we're trying to understand how these objects form. So I guess even if you're not in the field, you have seen these kinds of diagrams before. If you haven't, what you see here on the y-axis are the mass of different compact objects that were detected in different gravitational wave events. We have about 100 gravitational wave events that were detected so far. And each of these arrows connects kind of 2 compact objects that merge into a more massive one. So it's a really exciting thing. We're populating this diagram. It's the first time that we are observing such massive stellar mass black holes. We also observe some neutron stars that are merging. And really the key question here is, how do these objects form? It's not such an easy task to get 2 black holes to be so close together that they merge within a Hubble time. That's a really fundamental questions that we have now in the field. So this is a nice diagram that I stole from a recent review by Mandel and Broekadem. And I kind of flipped it. You're going to see it's very busy. I flipped it on its side. That's supposed to be the x-axis, but it's the y-axis here. And it describes the, let's see if this works. Yes. It describes the rate of gravitational wave events. First of all, these are observations over here. So as reported by instruments like LIGO, how many gravitational wave events we are actually observing. And now let's see what the different predictions are of different models that we have to explain these mergers. So this is a very busy diagram. You don't have to follow anything of that. All I want you to understand is that each and every of these lines represents a different model that we have to explain how these gravitational wave events form. This is a logarithmic scale for the rate. So we're talking about huge uncertainties, many models. So it's not that we have no idea how they form, is that we have way too many ideas and we don't know which of these ideas is correct. However, almost all these channels fundamentally depend on binary evolution. The most common, probably, channel or the group of channels that we have is called isolated binary evolution. You get a binary of black holes by starting with a binary of two massive stars that evolve, live their lives, and eventually become black holes. So let's look how such a binary evolution actually looks like. So when we start with two stars like these, they're going to initially orbit each other. They're not going to do too much to each other in the beginning unless they're very close. When you find such a binary in the sky, most likely it is still in the pre-interaction phase. So these are two stars that have not yet interacted with each other. But if you let this evolution continue, the more massive star of the two would evolve more rapidly. And one of the things that stars really like doing when they evolve is to expand. They want to become something like red supergiants, something like Lee Patrick here is researching. But in isolation, the primary star here, which evolves more rapidly, cannot just become a red supergiant. Instead, it hits its so-called Roche lobe. At this point, material is no longer bound to the primary star. It starts flowing away to the secondary object or even being lost from the system. A lot of different things can happen here. The primary in this simulation loses a lot of its hydrogen-rich layers. It becomes a hydrogen-depleted star. The second star accretes a lot of this material. It becomes a hydrogen-rich star, a rejuvenated star, we call it. And it also accretes a lot of angular momentum, and it typically becomes a rapid rotator. And as of this point, we talk about a post-interaction binary. So the evolution of these two stars is going to look nothing like what it would have looked like were they in isolation. And we distinguish between the mass donor and the mass gainer. If we let this evolution continue a bit, the mass donor will eventually contract on the thermal timescale until it becomes what we call a helium star. It would start burning helium in its core. It is no longer an expanded star. It's a really compact object, not a compact object, like not a neutron star or black hole, but it's a small star burning helium in its core. Sometimes we observe these stars. They often look like Wolf-Rayet stars. These are objects I work on a lot, but I'm not going to talk about today. While the companion is a rapidly rotating star. When stars are rotating rapidly, they tend to develop decretion disks, kind of like ballerinas. Yeah, they rotate so rapidly that the material kind of launches into the form of a disk. We call these kind of stars OE and BE stars. And if you ask someone like me, every time we observe such a star, it probably had to do something with binary interaction. They're actually very common, these stars. So we're still quite far away from having two black holes. Let's see how this continues. Eventually, this helium star would undergo through all phases of nuclear burning and collapse. Now, this is a key point, and a lot of uncertainty is happening here. Once the helium star collapses, and because of it developed an iron core that reached the Chandrasekhar mass limit, the star would either become a neutron star or a black hole. This may or may not be associated with a supernova. When I did my master's, I learned that all massive stars explode as supernovae. This is no longer the current state of things. We think that stars, especially stars that form black holes, might not even explode. Why is this so important? If you don't explode, then you probably are left with some black hole that is tied in this binary. And you will talk about a single degenerate binary in this case, a degenerate object bound to a non-degenerate star. If you do get an explosion, this explosion can kick away the compact object. So it is very fundamental for our understanding of how these compact object binaries form, whether or not there are explosions. If we survive this explosion, eventually the second star would also evolve. Here it expands, it can interact with the compact object. We can get a so-called X-ray binary. Eventually, if we survive all these explosions, we might end up with a binary of two black holes or neutron stars. So that's kind of the general idea of how we might form these compact object binaries, and all these processes that I just described are quite uncertain. So one of the big uncertainties, as I highlighted, is whether or not stars explode when they undergo a core collapse. That's a question that I'm going to focus on today. For neutron stars, we have quite a lot of evidence that they do explode, and we see neutron stars in binaries, like pulsar binaries. We see that they suffered a strong kick. There is little doubt about this, but for black holes, we don't really know this. The situation is much less clear. This is one of the theoretical predictions that exist in the literature, taken from Sukhbal 2016, where on the x-axis you see the initial mass of a star, and the colors depict whether, so a green color means that you get a neutron star and an explosion. Black means that you get a star imploding to a black hole with no explosion at all, so just vanishing and becoming a black hole. And every now and again, you see a blue color. This is an explosion and a black hole formation, which is rare. Few things to note. First of all, each of these barcodes is a different set of assumptions, basically. So there are a lot of uncertainties in how you explode stars. Generally, this is extremely uncertain. Exploding stars in simulations is very, very tricky. You need 3D computations. It's a very involved process. So we don't actually know what's the truth. But as you can see, these simulations predict that stars, let's say below 20, tend to explode. Above 20, they tend to become black holes and implode, but with many exceptions. Empirically speaking, we have very little constraints on this. And this is kind of what my focus is in today's talk, looking at this from an empirical angle. So how can we know if stars explode when they form black holes? We need to find black holes. How do we find black holes? Virtually all the black holes that we know are actually members of X-ray binaries. So the black hole is sitting next to a nearby star. Often it's a low mass star. Sometimes it's a massive star. And accreting a lot of material from the star and launches, has this accretion disk around it, and this accretion disk launches powerful X-ray emission. This is how we detect these objects. They're very interesting objects to study, but they have one problem. Because of the strong interaction, we don't really know what the conditions were when the black hole formed. So the star and the black hole interact so strongly that they kind of erase the pristine conditions that existed when the black hole formed. So they're not very ideal for studying this question of core collapse. What other black holes do we have? So another really exciting thing to look for are so-called dormant black holes that are floating around space, just roaming about. We actually expect something like 100 million of black holes to roam about space. And interestingly, we only know of one, a very recent detection. You detect them through what we call microlensing. So you have a black hole going, in the background, there is some luminous source, and you can measure the photometry and analyze it and conclude something about the mass of the lens. And it's a very difficult process. In fact, these hundreds of millions of black holes were thought to be maybe to constitute a solution to the dark matter problem. And it's still an open question if they are, but it's becoming increasingly hard to use black holes to explain this, but it's still an open question if this could be dark matter, actually. So the problem with dormant black holes, even if we could find them, and it's very difficult, is that they're just floating about space. They interact with the gravitational potential of the Milky Way, and we don't really know whether or not they suffered kicks. It's very hard for us to interpret their motion and understand how they formed. So really, the last kind of types of black holes that are really informative in this sense are dormant black holes, but in binaries. So kind of like X-ray binaries, but where the black hole is far away enough so that it doesn't interact with the star. And these are the sort of binaries that I'm going to talk about today. And as you'll see, they can give us a lot of precious information about how these black holes formed. Just need to mention that there are tens of thousands of such binaries we expect to exist in our Milky Way alone. So far, we know of only 2. So still very much in its initial phases. So why do we care about these dormant black holes? As I said, they do not accrete material from a nearby star. They do not strongly interact with their companions. So they kind of maintain the pristine conditions that existed when the black hole formed. They should be, at least in the massive star regime, they should be about 1,000 times more common than X-ray binaries. So they should be, in principle, more common than the objects that we know. But ironically, we have hardly ever observed them. And this is because they are hard to detect. They don't strongly emit in X-rays. We need other methods to find them. So we're talking here about this evolutionary phase, right? The 2 massive stars have evolved. And now we're talking about a star that is bound to a black hole. So it's a very interesting phase to look at. How common do we think these objects are? So here we kind of need to distinguish between massive companions and low mass companions. In a massive star regime, current predictions estimate something like 2 to 3% of the massive stars should have a black hole companion. It's actually an appreciable number. That means that if you observe the sky, you have a sample of 100 stars. Statistically speaking, you might expect 2 to 3 black holes to be there. For low mass regime, it's very different. If you have a sample of 100 suns, very unlikely you're going to have a black hole companion. So this fraction is an empirical estimate from one of the only dormant black holes that we know. So it's very, very rare. So if a friend of yours or a colleague runs to you and tells you they found a star with a sun with a black hole companion, you should be very skeptical. It's possible, but you should be very skeptical about this. How do we go about finding these companions and black holes? So from an evolutionary perspective, we expect this sort of system to reside somewhere in this regime. We're talking about, at least the regime where we typically care about, the regime of binary evolution, something that extends up to about 10 AU in physical separation of the companions. And here you see a bunch of observational techniques that we have to study different regimes of interest. Yeah, you might care also about things happening here. If you care about the regime of binary evolution, you mostly care about those 4 techniques: photometry, spectroscopy, astrometry, and interferometry. But it's really spectroscopy that kind of probes this regime most ideally, which is why for me, spectroscopy is kind of the bread and butter of what I do. And when we look at a spectroscopic binary, when we have a binary system of a star moving around something, when we take a spectra of this system, we're going to see the spectral features of the star or the stars moving back and forth in antiphase. So let's look how it looks like in real life. It doesn't look as nice as this. So here I'm showing you a real example for an object in the Large Magellanic Cloud. And we distinguish between 2 main types of binaries. The first one is called double-line spectroscopic binary, SB2. This is where we see both components. So I hope you can tell, these are quite noisy spectra, focusing on a specific spectral feature belonging to helium-1. And instead of just seeing one spectral feature static, we see this spectral feature being split back and forth in antiphase. And we can basically see both stars orbiting each other. These are really interesting binaries to study if we want to measure their masses, if we want to understand their properties, but they're not going to contain black holes, obviously. We see 2 stars. The other type of binaries are SB1s, single-line spectroscopic binary. This is just one example. You see one star that is moving. You can measure the radial velocities of the star. So it's clearly moving around something periodically, but you do not see the companion. And you look, you don't see the companion. This could have different reasons. Maybe your eyes are not good enough. Someone else can find the companion. Maybe this companion is very faint so that you cannot see it below the signal to noise that you have. Maybe it is a rapid rotator, so it has very broad spectral lines, so you might miss it. Or maybe it's a black hole. Maybe it doesn't emit any light at all. So single-line spectroscopic binaries are the place we want to look for these dormant black holes. That's what I'm going to focus on now. Now we need a sample of such single-line spectroscopic binaries, and there are different places you could look for such samples. One of the places to look is obviously the Milky Way, and this is being done partly by Spanish collaborators. But one of the attractive places to look in are also the Magellanic Clouds, and specifically the Large Magellanic Cloud. The Large Magellanic Cloud, if you haven't heard of it, is a nearby dwarf galaxy. It has a subsolar metallicity, so something like half solar metallicity. So if you're interested in low metallicity, it's a nice place to look at. And importantly, it contains tens of thousands of massive stars. And one of the famous regions in this galaxy is called the Tarantula Nebula. This is a famous picture taken recently by the James Webb Telescope of this region. And this region alone contains many thousands of stars. And for this reason, it has been the subject of various surveys. One of the big surveys in the field that we had is called the VFTS, or the VLT Flames Tarantula Survey. If you're familiar with the Flames instrument, basically you place it's a fiber spectrograph, and about exactly six epochs of observations were collected for about 800 massive stars in this regime to figure out whether or not they're in binaries. So that was kind of the first step. So you're going to see a quite exhausting tree chart here, just for a bit of statistics. Most of these stars, about 60%, were B-type stars, stars less massive than about 15 solar masses. I'm not going to talk about those today. They're interesting, and we still have some ongoing projects on them. I'm going to focus on the massive counterparts. So about 350 O-type stars, more massive than 15 solar masses. It has been shown by Sana et al. That you look at the radial velocities of these stars, and then you flag which of them seem to be binaries and which don't. And what they found is that about 35%, so about a third of the sample, were classified as binaries. The rest were classified as apparently single. Why do I say apparently single? Because we know our biases, and we know that among this population, actually a lot of them are still going to be binaries. The fact that we measure so many binaries with this data quality means that there are many more binaries in this population. I'm not going to talk about this population at all, but I did want to highlight this. I'm going to focus on the binaries, the ones that are flagged as binaries. For those, we had a follow-up survey called the TMBM, where this tree chart is going to stop now, I promise, which got many more epochs. Yeah, so we got many more spectra for these stars, for these binaries. And you can then classify them, as we have just discussed, to single-lined and double-lined spectroscopic binaries. So 40% of them were double-lined. You can see both stars moving in antiphase, fine. No black holes in there, obviously. We are going to look at the 60% remaining stars, that single-line spectroscopic binaries. So in total, we have 51 massive single-line spectroscopic binaries. That's what we're going to talk about. This is the sample in this gorgeous diagram. On the x-axis, you see the orbital period in log. So these are days. These are orbital periods of days. These are orbital periods of years. And we're probing a very wide regime here. So all these objects are stars that we see moving around something. We don't know what this thing is. On the y-axis, what you see is an estimate for the mass of the secondary object. How you get this? This is a bit involved. If I see a star moving around something, luckily we have Newtonian dynamics. If I can estimate the mass of this thing that I see moving, I can get a reasonable estimate for the minimum mass of the secondary star, and also estimate its mass. There is a probability distribution for the mass of the secondary, given the observables that we have. So for each of the binaries, we have an estimate for the mass of the secondary object. It's a logarithmic scale. I put some reference values here just to ease the eye, because logs are annoying. And these are quite large error bars, okay? And the question is now that I want to focus on is, where are the black holes? Yeah, one of the things we're really after here is to find these pesky, elusive, dormant black holes. How do we know which of these stars is a black hole? So you can approach this problem in different ways. What we did is something that turned out to be really successful, which is implement a technique called spectral disentangling. It's a bit technical for those of you who don't work with spectroscopy, but I have to mention it because it was kind of the basis of what we did. So when you have a single line spectroscopic binary, you might see something like this. You see a star moving back and forth. You don't readily see the companion. You might want to try and fit it with Gaussians, and you fail. This is what happens with all these stars. So what is spectral disentangling? It's actually a method that was developed originally in the 90s to deal mostly with double-line spectroscopic binaries, with the main goal of separating the component spectra. So you kind of push all your observations into some kind of an algorithm. There are different formulations for how this works. And the algorithm spits out two spectra, the green and the black. And when shifted in the right Doppler shifts, they should reproduce each and every of the observation. But it turns out that it's a really powerful method to use on single-line spectroscopic binaries as well, because it effectively boosts the signal to noise by the square root of the number of observations. You use all the observations together. In our case, this is almost a boost by a factor of 10. It's a factor of 7 or so. It means that we can see things that are much fainter than we could see if we were just looking at the individual epochs. So we can hunt for fainter stars. And we can also use this technique to measure the orbital parameters, and especially how rapidly the secondary is moving. So it's quite a powerful method. We didn't know a priori how well it will work, but it turned out to work very well. So this is, again, the sample I showed you before. Now let's see what happens if you implement disentangling. This was the main work. I'm not going to show you the exhaustive analysis, just the results. Everywhere where we see a green star in here, this is where a non-degenerate companion was found. So with disentangling, we could actually retrieve a spectrum of a second star. This is really cool. So for all these binaries, we actually have estimates for how the second star is moving. We can calculate things like the mass ratio. I'll talk a little about this. But mostly importantly, we know that these are not black holes, all these green stars. The light green stars are uncertain cases. They seem to be stars, real stars, but there are uncertainties. So we leave them as kind of uncertain. And where we have a yellow circle, I don't know why we chose this weird color scheme, but you'll have to bear with me. Where we have a yellow circle, this is where the second spectrum appears flat within the signal to noise, which means Either it's a very faint star that disentangling cannot retrieve, or it's a black hole or a neutron star, something else that we couldn't think about. You already see that some of them have black holes inside them, and we'll talk about those in a sec. I did want to highlight one point. This is not the main topic, but it kind of comes out of the study. One of the things that we found, because we have all these binaries, after you correct for biases and do a lot of stuff like that, you can look at the mass ratio distribution. So what is the mass ratio distribution of binaries? It's a really fundamental question. Not going to talk too much about this today. And what you find, the blue, this is a cumulative distribution. What you find is actually the mass ratio distribution of massive binaries is very close to flat. This means that for nature, it's just as equally likely to form a binary with two equally massive stars as it is to form with mass ratio of half or a quarter and so on. If you think about it the following way, if you have a massive star, it is actually quite likely for the companion to also be massive. This is very different than the initial mass ratio, than the mass function that really doesn't like forming massive stars. So this is just a neat result that I wanted to highlight. But now we're going back to the black holes. So I'm showing you the same diagram as before, but this time I threw away all the objects where we found non-degenerate companions. So we're kind of filtering the sample more and more and more until hopefully we'll find the black hole. So I'm left with all these uncertain cases and the yellow circles, which represent cases where we do not see a second star. And in principle, all of those could contain black holes. This is not likely, but it's possible. But one of them, we could actually show with the data that we have that it's clearly, well, there is nothing else that we could think about that is consistent except of a black hole. And this is this guy here, VFTS243. Maybe you already see why. It has quite a high mass. Yeah, sorry. Has quite a high mass for the secondary. And we'll talk a little about the system in more detail. Okay, so we singled this out to a different publication, and it turned out to be a really interesting system. So first, if you've been following the field, if you're somehow involved, maybe you heard of different black holes that were reported in recent years. Such dormant black holes, people are looking for them. We're not the only ones. And it turned out that many of these black holes that were reported were, in fact, what we call now black hole imposters. They had nothing to do with black holes. In fact, they turned out to be these weird, unique binaries that represent a rare phase of a binary system. And that's one of the things we did in Leuven, is actually to work on them, but not on, there were also contributions from Spain and from other independent collaborators and colleagues. So how do we know this is not a black hole imposter? I'm going to show you a bit how the analysis worked out. But one of the things that I wanted to highlight is that what we did here is to collaborate, basically all of us who have been debunking black holes before, not only people in Leuven, but also people like Karim El-Badri, who has worked independently of us. We threw all our tools and knowledge on this system to really make sure it passes all the tests. We got this kind of cringy title in the media, which is the black hole police. I don't really like it, but I do think it kind of represented the state of literature back then. So, okay, I'm kind of going to give you the main steps of how you go about proving that this thing is a black hole, or at least convincing yourself. The first thing, if you have your star, you need to convince yourself that you don't see a second non-degenerate companion. So these are really the spectra of this black hole system, focusing on a specific spectral feature belonging to helium-1. You can see it moving back and forth. It's quite a rapid rotator, so it's quite broad. The lines are quite broad. And okay, you don't see a companion. Maybe you can. I cannot see a companion here moving in antiphase. But what we really wanted to do is to do disentangling, right? And we disentangle the spectra. So here, for the first time and last time, I'm showing you results, how this disentangling looks like. So when you disentangle the binary, you get two spectra out. The red spectrum is the spectrum of the primary star. Okay, looks nice. The second spectrum is the spectrum of the secondary star. And what you see here is that basically it is flat. All the features that you see are of the level of the signal to noise. Ignore this. This is a diffuse interstellar band, has nothing to do with the star. So it looks pretty flat, and I'm contrasting this with what you might expect from a normal star of the mass that we expect the secondary to be. So it looks nothing like a star. All right. Now, in principle, it could be a sun. maybe it's a sun that is hiding in there. And of course, I'm not seeing it like a 1 solar mass star. So we need to get an estimate for the mass of the secondary. And to do that, we first need an estimate for the mass of the primary star. We have a couple of ways of how we measure the masses of stars. One of them, the cheapest way, is to look at the spectral type and kind of say, okay, this spectral type has this and this kind of mass. You can compute the so-called evolutionary mass, where you have the temperature and the luminosity, and you compare these two evolution tracks. There is actually a very nice tool called Bonsai that does that kind of for you in a sophisticated way. And probably the most robust way, but not the most accurate, but the most robust, in sense the least model dependent, is to compute the spectroscopic mass, meaning you look at the spectrum and you derive the temperature, luminosity, and gravity from the spectrum and the data that you have. And this is quite an involved process. I'm not going to talk about this, but after a lot of debates and experiments, we got this value. So you can see, basically all these values are consistent within 1 sigma. This one is with the largest error. What we did is the following. We took these two values. We dropped this because this is really, it's a bit complicated to explain, but it kind of depends on this. We ignore this one. Compute the weighted mean, you get 25 plus minus 2.3. It's a bit cheating. I don't actually believe that the real error is 2.3 solar masses, because we are worried about systematics. So the ideology of this paper is kind of to go for the 5 sigma threshold. We said, like, let's assume that the star is 25 plus minus 12 or so. So this is kind of the idea of the. Now you have the mass of the primary star. You can compute the following distribution, probability distributions for the mass of the secondary. You get the minimum mass of the secondary. This is this Gaussian here. The actual mass of the secondary, which has this funny distribution because of the inclinations. If you're interested, I can explain this, but I won't enter this. And the total mass of the system, which will be important later. The minimum mass is the critical thing. So what we find is that the secondary has to be 8.7 solar masses plus minus 0.5. Or if you go to the 5 sigma threshold, 6.5 solar masses. The secondary has to be within 5 sigma credible interval, at least 6.5 solar masses. Now we need to prove that nothing that weighs as much, that is not a black hole, can hide in the data. So you go and consider the different options. Maybe it's a normal star that weighs 8.5 solar masses. You take a model for such a star, plug it in the spectra, make mock observations with the same data quality, the same observational strategy, and convince yourself that you would be able to detect it with disentangling, which is this green spectrum here. Very easily, you find this star. It cannot be in the data. You go to the 6.5 solar mass limit, do the same experiment, try to disentangle. You get very clearly features in the Balmer lines that would be very hard to hide in reality. There are other types of stars. We talked about these helium stars, stars that can get stripped. We also considered those. This is a bit more challenging. We went to the 5 sigma threshold. You don't see it. And so on and so forth. We even considered the situation that the companion might be a binary in itself. This is an extremely unlikely situation because the orbital period is 10 days, but who knows? So we tried this, and even there we see this is very challenging, but you really see features that we do not see in the real data. So it really seems unavoidable that this guy is a black hole. One of the things that I want to mention is that finding this black hole it was exciting, but it wasn't surprising. We expected to find black holes in this sample. We talked about this before. Among massive stars, we do expect these black holes to exist. So it would have been more surprising to not find any. Okay, so we are quite convinced about this object. I highlight here the main properties of the binary. Now I want to talk about maybe the most exciting parameter here, which is the eccentricity. This binary is very close to circular. It has an eccentricity that is virtually consistent with 0. If you take this value seriously, you can actually estimate, assuming that there was a supernova explosion when the black hole formed, there is a very elegant relation that ties the eccentricity that you observe with the amount of mass that was lost during an explosion and the total mass of the system. If you plug in the numbers that we have, the eccentricity and the total mass, you find that 0.6 solar masses plus minus 0.4 solar masses were lost. Now, when stars implode or explode or undergo a core collapse, actually you expect between 0.2 and 0.5 solar masses to leave the star in the form of neutrinos. So this is kind of consistent with neutrino emission only. In other words, this system really looks as if the star directly collapsed into a black hole with no evidence for a kick or a supernova. If there was some kind of a supernova, it had to be very, very faint. It had to be a very small ejecta. So this is one object. We clearly need to increase this sample. Currently, we have a population of 4 dormant black holes. 2 of them are with low mass stars. They're really exciting objects, really interesting, but the problem is that we don't know how these binaries form. Yeah, nobody actually knows how to form a low mass star next to a black hole. It's an open question. And because we don't know this, interpreting these systems in terms of how the black hole formed is very difficult. For example, it could be that the black hole was captured at a later stage. In this sense, we cannot use things like eccentricity to interpret the kick and stuff like that. The other 2 black holes that we have currently in the literature that are kind of believed by the community are the one that I just talked about, and one that we kind of simultaneously found in the Milky Way. This was led by Laurent Mailly, my colleague. And interestingly, the other black hole in the galaxy, we still have more data flowing in for this just to convince ourselves, but it seems to be a very convincing case. This guy is in an eccentric binary, meaning it does look like the black hole suffered some kind of an explosion. So it could be that this is because of the different masses. It could be a metallicity thing. We still don't know. Yeah, we need to get more of these black holes to know. So I'm going to conclude a little by just talking about prospects of how we can find more of these dormant black holes. We clearly need them. This is the only way we currently have to advance on this question of kicks and supernovae. So you have already seen we have some other candidates, and we are collecting data for these candidates. For some of them, we still need to apply for data. So we might find a few more along the way. This is not going to be orders of magnitudes, however. We were really counting on Gaia to be a game changer here. This is something I haven't talked about today, but Gaia, using a similar philosophy, with high precision astrometry, it can tell if a star is orbiting something, and basically also you can conclude if it's a black hole or not. With the nominal uncertainty of Gaia, we predicted, and this was done by Sutkin, who is a student I co-supervised with Uksana in Leuven. She predicted that something like 200 massive stars with black hole companions should have been found by Gaia DR3. We actually found 0, so we were a bit off. And the reason for that is that Gaia DR3 was much more conservative than the nominal uncertainty. So we need to see if Gaia DR4 can deliver this thing. So there's still a lot to hope for. Another thing that is exciting in this context is to follow up on the sort of work we have done, but with many more stars. And this is something that can happen with all sky spectroscopic surveys. You have people here working on WEAVE. Here I highlight 2 of the surveys that I'm kind of involved in. One of them is Foremost, and the other one is MSE, which is still in design phase. We'll see if it actually launches. So yeah, it's going to be a lot of work. It's not going to be a straightforward path, but it's, in my opinion, one of the only ways to answer these fundamental questions about how massive stars collapse, whether they form supernovae or not. And this is it. So I'm happy to take any questions. Yeah.
Well, thank you very much, Tolmar, for that fantastic talk. I think it is on, Paco. Yeah, pretty sure it's on. Pretty sure it's on. Yeah. So yeah, thank you very much for that talk. That covered a sort of huge range of topics. Which so if there's any questions from the audience, we'll sort of take that first, and then we'll go to Zoom. That's fantastic to learn that we've got some online from Zoom, and we'll go there after this question.
Hello, thank you for the talk. I'm not in the field, I do biology, and I still was able to follow, so appreciate that. I wanted to ask about the aforementioned X-ray binaries. You said that these binaries, they kind of eclipse or delete the initial pristine conditions, and I don't really understand that. So what do you mean by initial pristine conditions, and how can they be erased?
All right, excellent question. You hear me, right? So there are 2 things that happen in X-ray binaries that delete the pristine conditions. Let's start with the more important one. You have seen that one of the ways we learned something about the kicks and the mass loss was through the eccentricity of the current binary. If you have an X-ray binary, per definition, the black hole is close to this, so close to the star that they tidally interact, and this tidal interaction circularizes the binary very quickly. So if you see a circular, actually all the X-ray binaries with black holes are circular, and the reason they're circular, as far as we know and we understand, is because of tidal interaction. So it has nothing to do with the supernova explosion and how much mass was lost. Additionally, the massive star is losing currently mass. The black hole is accreting mass. The black hole mass can change. So this kind of interaction also, yeah, we don't know how the black hole looked like when the supernova happened, because it now has different conditions, and the star itself as well. So for this reason, they are much harder to interpret in this context.
Thank you.
Yeah.
So yeah, so on that point, Tomar, I think you made a really interesting aside about the mass ratio distribution of these binaries. So how do you think that sort of comes about? Why do you think it isn't simply drawn from the IMF?
Yeah, that's a question for people who do star formation, and I'm afraid that if I say things I might say wrong. It has to do with the process of star formation, and actually it's an open question. There are different models of how these binaries form in the first place, and annoyingly, some of multiple models actually predict that you should get something like a flat mass ratio distribution. For example, you can imagine a situation where the more massive a star is, the more likely it is to attract a companion that is of higher mass or something like this. There are these kind of effects that happen as you talk about star formation. But I would not want to say more about this because I would probably say wrong things. Yeah.
Fantastic. Paco?
Yeah, a quick question regarding the period distribution. And so if you have an X-ray binary, you expect them to be very close in a very short period or whatever. What is the range that you think that your bias from your VFTS observations, for instance, that from which period onwards you could be missing by the sign of VFTS itself some candidates, let's say with between 5 days and 20 days. So would you expect there was some interaction already? So you had a black hole, but they're not close enough, so you don't have all the issues with the X-ray binaries. But wouldn't you expect at least a certain number of stars to be in this range of shorter periods? Would you pick them up, all of them with the VFTS?
You mean X-ray binaries specifically?
No, the black hole and the other companions, so that they are close enough, but not so close to be an X-ray binary.
Yeah. So for the VFTS, the bias starts dropping, or your detection probability starts dropping at about 100 days. Before that, we should be close to complete. Yeah, it climbs very quickly. So let's say if you talk about binaries of a few weeks, we should have detected basically all of them. Yeah, I think between 3 days and 10 days, I think we should be virtually complete, especially if they contain black holes, because these are the only thing we're not complete for are, polon binaries, which are very unlikely, or low mass companions, but these would not be black holes. So we should be complete in this regime. But actually the prediction is, which we don't know if it's correct, is that many of these binaries should have periods of the order of half a year, black hole plus massive star companions. So it could be that there are some others that were missed and they are in the apparently single box, actually. Yeah. Some of these.
Yeah, that's very interesting. Miriam, could you help with the Zoom? So, okay, so there's a question from Zoom that I'm going to read out here. Unless the person asking the question, Klaus, would like to unmute themselves and ask the question themselves.
Can you hear me?
We can just about hear you, Klaus, but it's a little low.
Can you hear me now?
You're coming through loud and clear.
Okay, so thank you for the talk. It's very interesting, the untangling process. And I wanted to ask you, how many lines do you use for it? Because I've seen that you use 4471, and I know that is a very metallic line, and we use it a lot. But when you try to get the spectrum, the untangling spectrum, you get mostly noise on the other lines in one of your image. And the question is more or less, do you use more lines to untangle? And if so, are the periods between the lines similar?
Okay, so I will try to kind of break down this question a bit. There is a weird noise in the background. Okay, when we disentangle the lines, it's a two-step process. The first goal, we know all the orbital parameters except of how rapidly the secondary is moving. So the first thing you need to measure or to try and deal with is to measure the radial velocity amplitude of the secondary. This you do by looking at individual spectral lines, and usually you would use the lines that are strong, and I would use, let's say in the spectrum we don't have that many lines, so I would use something like 5 or 6 lines belonging to helium-1, helium-2, and the Balmer lines. But when you do the final disentangling, after you have measured this radial velocity amplitude, you actually disentangle the entire spectrum. So what I showed you is the entire spectrum disentangled, and you look at the spectrum and you assess whether or not the spectrum looks like a star or not, which you could do subjectively or objectively. So I hope this answers the question, like something like 5 or 6 lines belonging to helium-1, helium-2, and Balmer.
Yes, thank you.
Yeah.
Okay, I think we have another question from Zoom. So Jesus, would you like to unmute yourself and ask that question?
Can you hear me?
We can
Yes.
hear you.
Okay. Okay, Tomer, that was an excellent talk. Yeah, I really enjoy it, and you explain things very well. My comment is actually on the previous question on the mass function, and there is one of the important things is that as I'm sure you know, you see this issue with the mass ratio. You don't see it only with when the companion is already a black hole. You see it already with when you see an SB2 system. So this flat mass ratio is also what we see when we do SB2 systems. And I think one of the most compelling ideas as to why this happens, why this is different from the IMF, is because when you're forming these systems, you initially have to formulate with already a relatively short period. So once you are having the cloud collapsing in order to form this, probably you need to dispose of a large amount of angular momentum on the orbital. So what happens is that you end up forming these two stars with similar masses, because otherwise you cannot dispose of the angular momentum. I think that is probably the most likely explanation among others.
Yeah. So on the last point, I agree. You're probably right. I don't agree with you, and I would be surprised if for SB2s you get a flat mass ratio distribution, for the simple reason that if you see an SB2 binary, then per definition the secondary is quite bright. And so I very much doubt that you would see, say, a mass ratio of 0.2 or 0.3 for an SB2 binary. So this is a highly biased population. Would you agree? Typically for SB2s, we see a trend, very strong trend towards unity, mass ratios of unity, which makes perfect sense.
Yeah, interestingly, actually, I think we see something similar for red supergiant binary systems, a flat mass ratio distribution.
But just by looking at SB2s?
Just by looking at the global population of red supergiants.
I think that the issue, we need to think about red supergiants, but generally the issue with SB2 is that per definition, you see both stars.
Yeah.
And so you will never see things that are extreme. Like if you put a massive star in the sun, I would never see it as an SB2. So how can I ever see a flat mass ratio distribution? Flat means that it's equally likely to get an extreme mass ratio, but I would never see an extreme mass ratio in an SB2. So it's kind of weird, but we can discuss this.
Great. So there's another couple of questions on Zoom, but before I do that, would anyone in the room like to ask a question? Got another question at the back there.
Well, thank you for the nice talk. I have a question. When you show before a slide, when you have all the evolutionary stage of a binary system, I've seen that what you are studying, which is a black hole orbiting another star, is like the previous phase of the X binary. So yeah, the high mass X binary. So you are studying the black holes,
yeah,
and without any emission. So it's always the previous step, or there are completely different systems?
It's a question for the philosophers. No, it's not. It's a question for us, but we don't really know. So in principle, if we talk about the regime of binary evolution, where these two objects are close enough to interact, in principle, with standard stellar evolution, you expect this star, this guy, to eventually expand. And it's kind of inevitable that it would interact with the compact object. But here, there is a slight detail. If it expands on the main sequence, kind of stably and slowly, and then suddenly it catches this black hole, this could actually happen with the system I talked about, then we would expect actually a stable kind of X-ray binary, the sort of things that we observe. If it expands after leaving the main sequence, which is the Hellsprung gap, it's very fast, then this is expected to lead to some kind of a spiral in and a merger, and probably you won't get an X-ray binary. So there is a lot of relationship between the dormant ones and the X-ray binary ones, but it's not. I would not sign on the fact that each X-ray binary must have been dormant once, and each dormant one would become an X-ray binary. I think there is some kind of a separation there. Yeah.
Thank you.
Okay, let's go to Gonzalo on Zoom. So Gonzalo, if you'd like to unmute yourself and ask the question yourself.
Can you hear me?
Yes. Hi, Gonzalo.
Perfect. Hi, Tomer. Very nice presentation. Congratulations. I have a small doubt and many questions, but I will choose one question and hope to find you with some time during this week. The small doubt is about photometry. If you find that this is an eclipsing system, automatically you eliminate the possibility of a binary hole, of a black hole?
Yes.
Okay.
Is that a question? Okay. Yeah, it's correct. Yeah.
I'm working with the photometry of Gaia. I'm hoping to find time to work with you about this. And the question was that you're using the idea that the mass gainer is getting faster, so it's a OE or BE, but your candidate, almost confirmed black hole candidate, is a rapid rotator. You say that it's a broad, has broad lines, but it's a rapid rotator. Also, do you use the rapid rotation as a consideration to eliminate a candidate?
So no, I do not use it at all. It is a very it is a very interesting piece of information. The fact that the star is relatively rapidly rotating. It's not a super rapid rotator. It's something like 200 kilometers per second. The V equatorial. It is interesting. It really looks like it accreted mass from the black hole progenitor. But I do not use this at all, and I would never dare to use it because rotation is not generally well understood. I would never use it as a criterion to decide if something is a black hole or not. So it's just a fact that we observe, but it has nothing to do with how we found this candidate. And just about the eclipsers, I just wanted to highlight on this diagram that I showed before, all the objects with a all the objects with a black circle, these guys, especially at short period, but also they're eclipsers. So it's kind of double confirmation that they are non-degenerate companions. So if you see eclipses, it cannot be a black hole.
Okay, perfect. Thank you.
Okay, brilliant. And I think we've got another question from Joachim Puls. So Joachim, if you'd like to unmute yourself.
Hello, everybody. So Tomer, that was pointed out a couple of times. This was really an excellent talk, and there are almost no questions remaining. So I have only two technical questions. The first question is, what is the minimum signal to noise you need to get a reliable disentangling? That's question number one. And question number two, I didn't get so much the point how Gaia comes into this game. I guess you mean that this is only, say, black hole candidates or something like this, and that you then like to do some follow-up observations.
All right. Hi, Joachim. The first question, the signal to noise, there is no answer I could give you because it fully depends on what you're after. You could do disentangling on spectra with signal to noise of 1.
Yeah, that's clear, but I mean with respect to your question.
To finding black holes.
Let's spectrum say.
So let's look at this data set. For example, we had individual signal to noise per resolution, per pixel, I think it was, of between 40 and 80, typically, about 30 epochs or 35 epochs of observation. And these are the results. We were able to find one candidate clearly. So it kind of seems like this kind of is the minimum that you want to aim at if you want to statistically be successful in finding at least one black hole. If we had a higher signal to noise, we might have, you see that there are other candidates like 779 and 514, which are highlighted there. If we had a higher signal to noise, let's say a factor of 2 or so, we should have been able to clearly say whether or not these are truly black holes. So yeah, I would say at least 50 if you want to have success, find at least one candidate like this, but yeah, something like this. The resolution of the instrument is 7,000. That's also 7,000, yeah. It's also important, there's an interplay, right? If you have a very high resolution, of course, you can go for lower signal to noise and you can do binning. Yeah, you can bin and you can, so this for 7,000, I would say roughly 50, the minimum that you kind of want to aim at, unless you're very lucky. Yeah. And the second question, the Gaia. So yes. Gaia, yeah, it measures high precision astrometry, meaning if a star is moving around something else, in principle, Gaia should be able to see this motion. It sees the motion of the PSF of the point spread function, basically. Now, how do you go about proving only with Gaia that it's a black hole? Actually, you don't necessarily even need spectra or follow-up for that. You can by measuring this motion, Gaia basically measures the orbital parameters, ideally, and you can compute things like the mass function, the astrometric mass function, and you can do some sort of diagnostic diagrams. And there are certain cases, if your star has a certain mass function, a certain orbital parameters combination, you can clearly say that there cannot be a luminous star in there. So it's a bit involved. It's not very easy to explain. And generally, it's better if you have follow-up observations. So the only candidate that was found by Gaia, it was a low mass object. And for that one, you could show just with Gaia that it's a black hole. But they also got, it was El Badri, and they also got follow-up spectra to show it independently with the spectroscopy. But you can really just prove it basically from Gaia alone.
Okay, thank you.
And this you expect to be more profitable in the fourth Gaia data release?
Yeah, what happened is that they decided to only release binary solutions that have an effective, let's say signal to noise or whatever of 200, like something they wanted to be super, super confident about the binary solutions. And they basically did not release the many, many millions of solutions that they had, which are sitting in some desktop somewhere and only a few people can access. So these solutions in principle should contain many more black holes. There could be a lot of false positives, but I wish they would have let the community to play with this data, but I don't know if they would release it in the next data release. So this is something I hope for, but I think they're still discussing this. Yeah.
Oh, fantastic. Okay, are there any further questions in the room? Anything else on Zoom, Miriam? And I think we've grilled Tomar for quite long.
Literally, it is very hot in here.
It's so hot. I mean, it's great that we've opened the door there, but I don't think you're feeling that on the stage.
No.
So yeah. So thanks again, Tomar.
Thank you very much for coming. So much for setting this up. Close your laptop.